Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everyone. It's a pleasure to introduce Tor Ahmet from University of British Columbia. Tor is an assistant professor there. Previously, he worked at the University of Toronto on hardware-based instruction and data prefetching with using speculative helper threads. And he also worked at NVIDIA on the memory system of GeForce 80 GPUs. And he's currently working on general-purpose graphics processing units. And he will talk about how to efficiently handle branch instructions in modern GPUs.
Tor? All right, thanks, Owner. Thanks for coming to my talk. Title is Leveraging Fine-Grained Multithreading for Efficient SIMD Control Flow. I was thinking after I sent the abstract and the title, I should have put GPU in it or something, but hopefully you'll get the idea that this is about GPUs. So just an outline of my talk. I'm going to start off by talking about performance of control flow intensive applications on GPUs. This is work that we presented at Micro in December. And I'll go through our baseline architecture assumptions, and I'll describe this branch divergence problem that we're trying to solve. And then I'll describe our solution, which we call dynamic warp formation and scheduling, and present some experimental results, related work and conclusions. And then I'm going to shift gears and talk a bit about my earlier work that I did while I was a PhD student. Just give a quick summary of that, which was on, as Owner was saying, helper threads. And then I'll briefly talk about some of my current research directions. Okay. Just some acknowledgements about this work that I'm about to present. This was done with the hard work of my graduate students. In particular, Wilson Fung was the key graduate student, but also a lot of help from Ivan Sham and George Yan. So I'd like to credit them with helping out a lot, doing a lot of the work. I just sort of supervised. So the motivation here is we look at it as GPGPU, which is taking general purpose applications and leveraging graphics processor hardware, commodity graphics processor hardware to run other things that are non-graphics. So as you all know, GPU is a massively parallel architecture. And as many of you are probably aware, it uses a single instruction multiple data pipeline. And the reason for that, the motivation, is to basically squeeze more computation out of a silicon budget. So if you look at this graph, it's just showing you versus the year on the bottom here, the number of gigaflops, the peak gigaflops you could get out of the hardware. And as you can see, around 2003, the raw computing potential of a GPU sort of surpassed what you could get out of a high-end CPU, even if you were to use the vector instruction extensions. So again, the goal here, we want to take GPU, which is really designed for people playing video games, but apply it to non-graphics computing. And there are many challenges to doing that. I mean, key challenge is how to program. But in this work, we're going to focus on a hardware mechanism for how do you get, for efficient control flow, for programs that have a lot of control flow. That's our goal here. So let's just start by looking at the programming model that we're assuming. If you look at how you program a GPU to do graphics, this is sort of the high-level view of it. You start off with something like OpenGL or DirectX, and you write your application. The GPU is going to take that, and it's going to run, it's going to take triangles, and it's going to decide maybe to change the triangles a bit with something called a vertex shader. And then it's going to color in pixels using something called a pixel shader. And the goal is, with the pixel shaders and the vertex shaders, to get more realistic illumination effects and more realistic visual appearance. So, on the far right here, you see like a very realistic rendering that you're trying to get. So we're going to use the hardware that does all this stuff to do programming using something that's basically C. So some of you may have heard of something called CUDA from NVIDIA, which is basically C for GPUs. And it's more easy to program, I would say, than some previous versions, things like CG. What it gives you is it really hides a lot of the SIMD pipeline from the programmer. You don't need to know like the vector width of the SIMD pipeline. The only place where, as far as we've been able to tell, that the SIMD nature of the pipeline becomes visible is if you try to start synchronizing between scalar threads. So the programming model, single program, multiple data. So you have multiple threads all executing the same program in parallel. And this puts a lot of the work in the programmer's hands. They have to express a lot of the parallelism using these threads. If they don't do that, then you're not going to get the performance. So this, this whole approach also is very similar to what's called stream processing. Okay, so our paper at Micro, we call it dynamic warp formation scheduling for efficient GPU control flow. So we have to define this term warp. I'm going to use it a lot in this talk. Warp is a term coined by NVIDIA, which is a group of threads, scalar threads grouped together into an SIMD instruction or a stream of SIMD instructions. And why warp? Are we talking about Star Trek? Not really. This is, I think the motivation for this term was from this definition here. Out of the dictionary, a warp, and some of you may be aware from the textile industry, refers to a bunch of parallel threads, essentially, stretched lengthwise, and then there's a weft that goes the other way. So kind of a clever play on words. Okay, so here's just an example to motivate the branch problem that we're going to solve. So we're going to use, again, we're using a SIMD pipeline to save area on control logic. We're grouping scalar threads into warps. And so this diagram here off to the right is going to hopefully illustrate that for you.
When you say save area, are we talking about transistor area on?
Yeah, we want to support more threads per unit area of silicon.
Okay.
Yeah. Okay, so at the top here I've got this blue box, and inside of it there's a bunch of arrows. The arrows represent different scalar threads grouped together into a SIMD instruction grouping, or a warp, as I'll call it. And they're starting off executing this control flow graph. This picture here is of a control flow graph, and you can see there's a branch in the middle that's going to go either left or right. And so when the thread comes along, it reaches the branch, and some of the threads want to go to path A, and some of them want to go to path B. So this is this branch divergence problem that we're trying to solve. So here we see schematically, some of the threads can go ahead, and they'll execute the instructions from path A. But the threads that want to go to path B have to wait. So the SIMD pipeline can only handle one instruction type at a time. So we're going to execute the instructions on path A, and then later we'll come back and we can do the instructions on path B. And there's a number of ways you could implement that. Okay, so but the key thing to note here is that while the paths diverge, we're losing efficiency of the hardware. There's these empty spots here where the hardware could be doing some computation for us, but it's not doing any computation. Okay, so what we measured across a bunch of general purpose non-graphics applications is that if you had a SIMD width, that means 16, or SIMD width is the number of arrows here of 16 elements, or 16 scalar threads grouped together, that we would get a roughly 50% performance loss at that sort of width of hardware. And it gets worse as you go to wider SIMD widths.
Could you give an example of one of these applications, these non-graphics applications that's still amenable to SIMD processing?
Sure. So I'm going to show you some results later, and I'll go through some of the benchmarks. One of them is HMMer, which is used for bioinformatics for sequence matching. Okay. And yeah. Okay. So here's dynamic warp formation. This is the key solution that we're proposing, and just at a high level, and we'll go into details later. So here we're going to note that the hardware is going to have a whole lot of threads, more threads than we can fit into one SIMD or warp. And so because of that, we're going to multi-thread, and we're going to have multiple of these SIMD instruction threads going at a time, and they're going to be time interleaved. So here is just one of them coming down to this branch, and it comes along, it hits the branch, and it diverges. And now here's the second thread of scalar, or second warp, if you will, of scalar threads coming along, and it also comes up to the branch and it diverges. And when it diverges, it's going to diverge somewhat differently. It tends to, we found, diverge somewhat differently. So in the blue case here, the set of blue threads, you see the arrows here line up, the first one and the third one, etc. And in the second warp, it could be, for example, that the first element doesn't go to path A, but the second one does. And so we can see that there's some opportunity here, represented by these green squares, where there's some overlap, right, where we can merge things from one warp into another. And that's really the key thing we're going after here. So we're hoping to take these two warps that have diverged and then from them create new warps, ones that have more, that use more of the SIMD hardware on a given cycle. So our results show that we're getting 20.7% speed up with a 4.7% area increase. So that's the result that we presented at Micro. And so the rest of the talk is going to be how do we get to this? How do we actually implement this?
What kind of control flow graphs are these usually? Can you predicate them?
These are
The branches?
Yes. So alternative for getting some of the alternative to our baseline implementation would be to use predication. Predication, though, does have the inefficiency. So when I have some instructions that are predicated off, they're not using effectively. They might have used the hardware, but we threw out the result, right? So, but in terms of limitations on the control flow, there aren't any. We could have irreducible control flow, and we'd be fine, et cetera. Yeah. So it could be very arbitrarily complicated control flow.
So the 20%, was there a particular application?
That's average harmonic mean across a bunch of applications. So I'll get to the data later in the talk. And
some applications probably did much, much better.
Yes, and some didn't see anything, right? So we include the ones that didn't see anything as well. Yeah. Okay, so our programming model that we're assuming is the CPU is going to spawn off a parallel section of work off to the GPU. And then when the GPU is finished doing some processing, it's going to return control back to the CPU, and the CPU will do some more stuff. You could generalize this. You could have the CPU do something in between while the GPU is doing something, but we didn't go that route for simplicity. Over here on the right-hand side, this is what we're assuming the GPU looks like. So there's going to be multiple shader cores. There's going to be some sort of interconnection network, and then there's going to be a high bandwidth memory subsystem feeding all that, keeping it well fed with data. Okay, so let's just sort of look at a core, zoom in on one of these cores here and see what it's doing. Okay, so we're going to have multiple thread warps. All threads, again, running the same kernel of the data parallel section. Again, a warp is going to be a bunch of threads grouped together into a SIMD instruction. And the idea here is we have one SIMD pipeline, and we're going to do multi-threading where we've got a bunch of thread warps ready to go. They're ready to be executed on the pipeline, and then we're going to select each cycle. We're going to select one of these thread warps and execute it on the SIMD hardware. So here, okay, thread warp. What does it look like? We've got a common PC, so all the scalar threads are executing at the same instruction here, and you could.
Program counter?
Yeah, program counter. Sorry. And then so that way that they're always executing the same instruction at a given clock cycle. So here's how that looks like when we add in the rest of the pipeline. So this was sort of the last figure, just the thread warps ready to execute. The rest of the pipeline is we're going to fetch instructions, we'll decode them. So because it's SIMD, we can do one fetch and one decode for all the different elements in the vector instruction. And then we split up into the vector lanes here, you can see schematically. And then we're also going to have parallel access to the data cache. And the key thing here is, because we're assuming we have large data sets, there'll be a large number of cache misses in the data cache. And so very often, a warp will go through the pipeline, get to the data cache, it'll find that the data it wants isn't there, and it won't, if we stop there, the pipeline would all stall and we wouldn't be doing much computing. So what we do is we take the warp out, we sort of put it aside, and we say, we'll let the memory access proceed in parallel, and we'll try to do something else. We'll use some of these other threads. So very typical approach, use multi-threading to hide memory latency. Okay, so the motivation of the multi-threading here originally is hiding latency. Now we're going to exploit that multi-threading to also improve the control flow. Okay, so we're, again, so one thing I'll just point out here is that the register file here is massive. Okay, it's really a huge area consumer. So we need 100 to 1,000 threads, and each thread, while it's sitting over here waiting for memory access to complete, has to keep its register values in the register file nominally. And the need for hundreds to thousands of threads is easy to satisfy in graphics, right? Because there's millions of pixels, right? It's a little bit of a challenge. Could be a challenge for general purpose or non-graphics. Okay, so let's take a look at the branch divergence problem in a little bit more detail. So here I've got a control flow graph a little bit more complicated now. Here's like an if-then inside of an if-then and a loop. And so let's imagine we have a a bunch of threads. We'll have 4 threads, and they all want to execute on this hardware, or execute this control flow graph. So thread 1, let's say, wants to go A, B, C, E, G. All right. Thread 2 wants to go A, B, D, E, G, and then thread 3 also wants to do the same thing. Thread 4 wants to go over here to F. Okay, so that's what we'd like our scalar threads to do. The question is then, how do we do that all with one common PC, right? So one solution might be to go and do some sort of predication thing. The approach that we're going to take is a slightly different approach, which I'll explain in a second. But before I explain how we're going to do that, let me just give you some high-level results. So I mentioned earlier that if you go and as you increase the width of the SIMD pipeline, you get this inefficiency. But that, due to that branch divergence problem that I just illustrated, as you go to wider and wider SIMD pipelines, it gets worse and worse. Okay, so here up at 16, we've got 50%. With a narrower SIMD pipeline, it's less. So one way to, a different way to solve the problem is to go to narrower SIMD pipelines.
That costs you a lot more silicon.
Yeah, yeah. So that was well known, and so we started looking at, what is the source of the problem. And so one thing that we initially thought was maybe there's a way that we could reconverge threads differently. So you notice in this example, let me just scoot back here, that all these threads sort of reconverge down here at the bottom. And so one thought is, well, I'll let one thread go, and I'll make it wait down here at the bottom, and then I'll let another thread go and make it wait at the bottom, and then the next thread go. And when they all get back here, I can sort of get them all to make one happy family again and go together back to the next iteration of the loop. And so the thought was maybe, where we pick this reconvergence point has some impact. So we did a study, and we, there is some sensitivity. Some applications actually have some sensitivity to where you pick the reconvergence point. And so the nominal thing is to sort of wait at the next next immediate post-dominator is what we chose. Next join point is a little bit vague. And what we found is that's not necessarily the best place. We did a bit of a limit study, and we used a sort of a test example, sort of pathological, to show that we were getting something that made sense. And we found, though, for real applications, this really wasn't where, this wasn't a way to recoup the efficiency or inefficiency.
So we have PDOM and Oracle.
Yeah, yeah. So PDOM is post-dominator, immediate post-dominator reconvergence at the immediate post-dominator, which I'll show an example in the next slide. And Oracle is saying, if I found the perfect reconvergence point by we use sequence matching to find sort of the perfect place to reconverge the diverged threads, what kind of IPC would I get? And so yeah, so you can see here, this is showing IPC. You could get full, for this pathological example, you could get a lot of, you could recoup a lot of performance by picking the optimal reconvergence points that way. But for real programs, we didn't see much of a difference. Yeah. Okay. So really the more common problem was early loop exit for some subset of the threads in a warp. That's what we discovered while we were doing this. So here's our baseline that we're going to compare against. And this, effectively, you could argue a predication might give you something similar to this. But this is how we simulate things in the hardware. And other people have proposed similar mechanisms to this. So this isn't really our reconvergence mechanism. Or this is in our dynamic warp formation mechanism. I'll present that later. This is just the baseline that we're going to assume. How would you implement this? How would we build hardware so we can support the branch divergence amongst different threads? So what we're going to have in the hardware is we're going to have a stack. Okay, the stack is going to have a couple of fields in it. One is just the next PC for the SIMD warp. The other is going to be an active mask saying which threads are actively executing on the hardware. And then we're also going to have a reconvergence point. So when we reach a divergence point, we'll have a pointer or an address that will track which is where we want to reconverge. Okay, so let's just go through this example here where we've got 4 threads, scalar threads. They're grouped together in a warp, and they're starting at basic block A, and they're going to diverge. Okay, so we get to A, and we have 3 of the threads want to go to B, and 1 of them wanted to go to F. So what we have here is we push onto the stack that F, one of the threads here, this lonely thread, wants to go to F, and the reconvergence point we're going to use is the immediate post-dominator. of the branch. So which is sort of the point here, which all paths leading out of A have to go through this point, really, and this is the closest such point where all paths leading out of A must go through. We'll push that on into the stack as our reconvergence point. We'll say the next PC, when we get to it, is going to be F, and then the active mask will just be for that last element. We'll also push onto the stack the threads that want to go to basic block B here, which is the other 3 threads in this example. And so again, they're similarly going to want to reconverge at G, and we've got this next PC of B. Okay, so now these threads go along, and then they diverge as well. These guys are now executing at B because they're at the top of the stack. We have to come back to F to execute when we pop that off the stack. So when we get to B, we're going to diverge again. We have 1 thread that wants to go to C, and then 2 threads that want to go to D. So again, we push onto the stack the 2 threads that want to go to D, and we also push onto the stack the 1 thread that wants to go to C. And we see that the reconvergence point, because we're diverging at B, we can reconverge a little bit closer. We can reconverge here at E because both of these paths reconverge here.
Can you go to the previous slide?
Yep.
That wasn't the previous slide.
Yeah.
I meant one flashback.
Okay, previous animation.
Right.
Here?
On the stack,
Mm-hmm.
we've got B. Somewhere along we changed that to the next PC on the current that line where
Yeah.
it says B. When you flip the thing, it
Yeah,
not
here-
the other way.
Okay, so here was A, right? And yeah, so I think what you're picking up on is we changed the next PC here from A to G.
Right.
Right. So after we finish executing A, the next PC after we finish the divergence will be G. So once we popped all this stuff that's on the stack off the stack, we're going to be executing at G, and everything's going to be reconverged. So that's how that works. Yeah. Okay. Okay. So we were.
These instructions carry reconvergence?
Yes. So when you have a branch, you'd have to have this encoded as like an extra field, or you could have maybe a table. Yeah. Okay. So here we're at C, right? Once we get to C, the next instruction at C would be E. Okay. So we'll notice that C, the next PC is E, and we'll pop off this entry off the stack. Okay. And so then we'll execute the next thing on the stack, which is D. Okay, so we'll execute that. We get to the next PC, which would be E, so we can pop this guy off the stack now. And so now we're at at E. We execute this guy, and once we're done with him, we're at G again, so we'll pop this entry off the stack. We'll see there's a match between the next PC and the reconvergence PC. So then we get to F, and we finish executing F. And next PC again is G, so we're done. And then so we're back, everyone's back together again here, and we advance the next PC, we get back to A. So that's our baseline mechanism. And again, there's a lot of inefficiency you can see here. There's a lot of, if you look at the time diagram at the bottom, there were a lot of time slots where there were SIMD units that weren't actually doing computation. So that's what we're trying to solve. So this is our baseline. So dynamic warp formation, the key idea again is we're going to form a new warp when we reach a divergence. We're going to look for multiple warps. And again, these exist because we have so many threads that we can't just encode all the threads into one vector instruction stream. We need to have multiple of these things, and they're going to be fine-grained multi-threaded on the hardware. So we have enough threads here branching to each path, okay, to create, the goal is we have enough threads to branch into each path to create a new full warp. And in this case, we show, here we're going to try and fill out this warp with more things than either of these two. So there's a few key things here, right? You could have this situation where when I have 2 of these diverged warps, there's some overlap, right? So some of these guys overlap, and so that means that we can't necessarily merge them completely together. But what we found is that if you have enough of these warps, and you tend to, in order to be able to use a GPU effectively, you need to have a lot of these anyways just for the memory system. So you'll have a lot of these anyways, and at the end of the day, you're going to find that you're reducing the total number of warps that you need. Okay, so what that means is that when you're executing any given cycle on the hardware, you're using more of the actual ALUs. Yeah?
I don't have a real intuition what the sort of columns in each of these
Okay.
blocks mean.
Yeah, so the columns are scalar threads.
But is there any reason why when you're converging you couldn't move them left or right?
That's a good question. It comes down to the hardware and where the register values are on the hardware. So you've got different vector lanes, and so if I move them from one column in this figure over to another column, that would actually be switching a vector lane. So then I'd have to transfer the register values from one lane to the other. Yeah.
So it would require a different hardware structure to generalize this, where you say, okay, I've got 100 threads, and every one of them has their register values, and I don't care which ALU they're actually running under.
Yes, so we've generalized it to that, we've generalized it halfway. And I'll describe the hardware mechanism that we proposed a little bit later. I think that's probably a better time to show you that. Okay. Okay, so that's the key idea. Here's an example. So here, if you look at what's inside the boxes on the left-hand side here, we've got two threads, or two warps, X and Y. So this is two SIMD warps. And they're sort of time interleaved. They're going to go through this control flow graph in a time interleaved fashion. And here on the bottom, I'm going to do sort of a time, execution versus time of the two different techniques. One is, the top here is going to be the baseline, and the bottom is going to be this dynamic warp formation idea. So we'll just go through the first one here. Okay, so we have, first we'll have, and this is sort of color-coded. So we've got X is going to be blue and Y is going to be red. So you can see as you go along here, time interleaving, we're going to do first X, and then we're going to do Y on the pipeline at A, and then we're going to go to B, and we're going to do X, and we're going to do Y the next cycle. And again, there's going to be some inefficiency here. Then we'll do C, X, and CY. And then we'll come back, as per the baseline technique, we'll come back to D here. We'll do the X warp, and then we'll do the Y warp. And then we'll come down to E, and so on. Okay, so that, again, there's all this empty slots that are inefficiently, or that lead to inefficiency. So the key idea with the dynamic warp formation is we're going to create this new warp. Okay, so on the bottom here, let's see how that works. So when we reach that first divergence point, we can create a new warp here. And key thing is we couldn't actually use up all of the, we couldn't merge the two warps completely together. So we sort of had this sort of half-empty warp left over. So it doesn't always work, but it works enough of the time. So the next example here, when we get to C, we could completely merge these two warps. So here we've got two elements in this warp that are actually active, and instead of having two separate warps with one element active. So that's much better. And so there's several examples like that. If you go on to D, again, we have another example where we've merged both two warps into one. Okay. And same thing here at F. Okay. At F, we had, again, no overlap, so we could merge these things in. All right. Okay, so that's an example. It's, again, high level. So the next sort of question is, how do you build the hardware that actually does all that? So this is a slide here showing how we actually build the hardware. So here's sort of the baseline pipeline. I showed this earlier, but now it's sort of rotated. Here we've got the instruction cache, and then we've got a decoder, and then we've got these different vector lanes, and then we've got the end of the pipeline here, commit. And so we were going to add some extra hardware, which is shown here at the top, and this isn't like to scale, so the fact that the top is bigger than the bottom shouldn't frighten you. This is more for ease of explanation. So we're adding three key hardware structures here. One is the warp pool, and that's where new warps are being formed and ready to go and issue onto the pipeline. And the other thing is the warp update register, which is where we're going to take warps that are committing, like branches that are instructions that are committing that have diverged, and we're going to figure out what to do with them. And in between these two, the warp update register and the warp pool, we need some sort of level of indirection to sort of tie them together. So we've got this thing we call the PC warp LUT, which is basically when I have something commit and I know it's diverged, where in the warp pool should I put it? This is just sort of going to help me figure out where to put it. There's another thing, there's other few structures here. We have some issue logic which figures out which warp we want to issue next. And we also have to figure out how to allocate things into the warp pool. So we have an allocator structure. So I'm going to go through an example here, hopefully give you some intuition for how this works. So here at the top right, there's a little code example, very simple, just a branch instruction. And so we can branch, we're at A, that's the program counter, and we can either branch to B or we can fall through to C. So that's the example we're going to look at here. And let's imagine that in the warp pool we've got two warps. We've got, both of them are executing branch A. And here's some thread IDs. So each each lane here is going to have a thread ID associated with it, and they're just numbered sequentially 1, 2, 3, 4, and then the next warp is 5, 6, 7, 8. So when we start, we're going to select the first warp here, which we'll call X, and that's going to go and start going down the pipeline. Okay. And then next cycle we'll select Y, and so they're going to both be going down the pipeline sort of one after the other. And we'll notice, okay, so they're going to access different register lane or different vector lanes based on where they are in the warp. So we get to the end of the pipeline, and we'll have noted that there's some divergence. This is a branch instruction. Some of the elements wanted to go to B, and some wanted to go to C. Okay, so when we get there, what happens is we're going to note we have these two registers here. We're assuming, for simplicity, that there's sort of two outcomes of the branch. If you have a multiple, if you have like a jump indirect, you could pipeline this over multiple cycles, or do this over multiple cycles. None of our benchmarks had that. Okay, so we'll assume two different branch outcomes, and so we have these two warp update registers. So the top one is saying, okay, I've got these elements here in the middle of the vector went to B, and so these are the thread IDs. So this is sort of like a valid mask in the middle here, and we've got on the bottom we've got these two elements went to the next instruction C, and we've got the thread IDs. So then what we're going to do is we're going to look into the warp LUT, and so the warp LUT is basically going to track for a PC. So this is like a fully associative, or you can think of this as a cache basically. You're looking up based on the PC of the next instruction, and you're trying to find if there's something allocated there. If there isn't, you're going to allocate a line, and you're just going to track what things have been, which threads in that warp are currently occupied. Yes?
So is it one way for each PC you have at most one line in there? And when
Yeah.
you build it, you pick it out?
Yeah, I guess we could, I think that's probably how we would have implemented it. I think we use like a set associative cache actually for this, 4-way or something. So yeah, the PC would show up once in this structure. Yeah. And okay, so the reason for that is then we're going to have an index. Okay, so this index is actually a pointer to where in the warp pool we're currently forming a warp at that next PC. Okay, so here we've got index 0, which points to the first entry in the warp pool. And so what we've done is we've taken the thread 2 and 3 and we put it into that first warp there. And we'll see that there's still some unoccupied slots in this warp represented by the zeros here. Okay. And so similarly, we're going to do the same thing with this warp at the bottom. Okay, so warp the threads that diverge to the next instruction C are going to have a different entry because they have a different next PC. And they're going to also allocate a different entry in the warp pool here. And so we've got a different mask and a different offset into the warp pool. So this is, you can think of it as sort of an index structure, index based on this value here. Okay, so that's fine. Now let's, okay, so we also, that was just for the first warp, the warp X. We also have, right after warp X, we have warp Y, which is just finishing up. It's also executing the branch, and it's going to diverge as well. Okay, so it diverges, and now, so we've overwritten the values with these new values here in the warp update register. These are the outcome of the branch for warp Y, and we've got, for the top, for the threads going to next instruction B, we've got thread IDs 5, 7, and 8, and for the threads going to next instruction C, we've got just thread 6. And so what we're going to do now is we're going to look up using the next PCB into the warp, the PC warp LUT, and see what's there. And we'll see here that if we take the mask here and we compare it to the mask here, we do a set difference, we can see that 2 of these threads can be merged into whatever is currently being formed in the warp pool for B. So that's what we'll do, is we'll update the row we were looking at previously, and because 5 and 8 don't conflict with what's in there already, we can add them to this warp. This thread 7 unfortunately conflicts with something we already had in the warp, so we have to allocate now a new warp for 7. So now we're going to allocate a new entry in the warp pool, and we'll update the entry for B in the PC warp LUT, and we'll indicate that now in this new warp we've only got 1 thread active, or 1 thread slot that's been occupied.
Or we have 3 available in case we're in a third warp is really what it's for.
Yes. Sorry?
In other words, the purpose is to show us that
Yeah, exactly.
In case there was a third warp.
Exactly,
coming along.
exactly. Yes,
So
yes.
the purpose isn't to show us what's filled as much as to show us what's available.
Yes.
So the cup is half empty.
That's right.
In this case,
half,
quarters.
yeah, half full. Yeah, no, you want half empty, right? Okay.
The more empty, it's better if you have another guy come along.
Sure. All right. Okay. So C is similarly. We're going to come along. We're going to see that we have an available slot here, and so we're going to merge that in here. Okay. So now let's take a look. We'll go one pass through with a merged warp. Okay. So now we're going to take this new warp that was being formed for B, and it's going to go through the pipeline. And we'll note here, okay, as it goes through the pipeline, we'll call this warp Z now. We'll give it a new name. That as it goes through the pipeline, we'll notice that the threads are still in the same lane that they were originally. So that's key because we want to make sure that they can access the values in the register file very easily. Okay, and so this mechanism allows us to avoid the problem of bank conflicts, which would be where multiple threads that want to access the register file in a given clock cycle have to access the same bank to get their register values. Which would then slow down the throughput of the machine because we'd have to serialize the accesses.
Unless there was a different hardware mechanism, which would be a different talk.
Okay, so here's the possibilities, right? So one thing is we could have the ideal mechanism here on the left-hand side, which is we have an import register file, and so maybe you could somehow, with multiple different warps accessing things, we could just access them in parallel. That would be the sort of ideal thing. And we wouldn't have that problem. But that becomes very area expensive, right, to have an import thing where you have 16 ports. I don't know if anyone's ever even built something like that. I guess maybe, but not for a register file. And another alternative is to have like a crossbar between the decode stage and the register file. But that again has this bank conflict problem where we could have multiple threads here. They all want to access one register file lane, and so we'd have to serialize. What people do in sort of the existing approach is you have all warps. They all want to access the same row here in this register file. Okay, so they're all sort of grouped together. And how we're going to pick out a row in this register file is based on the warp ID or the thread ID, if you want to think of it as that, and then the register number. So we'll take those two numbers, you can concatenate them if they're power 2, and use that as an offset into the register file. But because we're mixing and matching threads around, we can't really use that mechanism anymore. So we have to actually add a separate decoder now per register file lane and allow each lane to have its own different offset based on the warp ID changing. They all have the same register ID because it's all the same instruction happening on each pipeline. But now because they're going to have different warp IDs because they're being moved around, or different thread IDs, we're going to have different offsets into the register file. So that's sort of a implementation detail. So now I'm going to just go on to experimental results section. So what we did for this study is we created a cycle-accurate simulator starting from simple Scalar. It's almost an interesting talk just to explain how we did that, because simple Scalar isn't a vector instruction set, so how do you do all this? We selected some benchmarks from Spec 2006 and also from Splash 2, and we also looked at some CUDA demos that NVIDIA had put on their website. And so the key thing was, for the benchmarks that were sequential is we had to manually parallelize them. And we're manually parallelizing them using a programming model very similar to CUDA, which is like the SPMD programming model. Our hardware is described here in this table. We're assuming 8 cores with a SIMD warp size of 16. We're assuming 256 threads per shader core, and here's a bunch of parameters for our timing simulation for the memory system. Okay, so here are the results. So baseline is the yellow thing here, and orange is the dynamic warp formation, and we're showing IPC, so higher is better in this chart. And these are the different benchmarks we evaluated. So some people were asking about that. So we've got HMMer, which is a sequence matching, LBM, which is another Spec 2006 benchmark. Black is Black Skulls, which is options pricing. Bytonic is a sorting kernel. FFT from, I think this one was from Splash, and LU factorization, and then matrix multiply, and the last thing here is in a benchmark, it's the harmonic mean. So we can see here that we're getting about 20%. If you look at the harmonic means, we're getting about 20% on average improvement. Now, one thing we note here is Black Skulls wasn't doing so well, and I'll talk about that in a second. Another thing we did here was we compared against a machine that's sort of idealized, has the same number of ALUs, but it's a SIMD machine, meaning each ALU has its own sequencer, can have its own program counter. And so just to see what, theoretically, what's the best we could do in this situation. And so we see that we're getting pretty close. If you look at the harmonic mean here, we're getting pretty close. We've really closed the gap between the baseline and the sort of ideal machine quite a bit. And so you might wonder, like, why don't the MIMD machines all have sort of the same IPC here? And the difference is the memory system. Yeah?
So, okay, I guess the model of the MIMD is you're saying, well, if we ignore the fact that this costs more area, this is our goal. So I expect that to outperform everything, but FFT is a little lower.
So this is actually a second order effect with the memory system. When you allow the threads to kind of go their own route, then you get interactions in the memory system. Basically what people call like the coherence problem in the graphics world, but not the same coherence problem from the CPU world. Is the DRAM, all these accesses are going to totally different DRAM pages, basically. So it just results in DRAM inefficiency. Okay, and also it can affect in the caches too. You have higher cache miss rates. Okay. So again, I mentioned Black Skulls took a bit of a hit, so we went and dug in a little bit deeper into why that happened. So this model here is assuming with a very detailed model. The next slide, we simplified our performance model. We ignored the lane conflicts, and we found that was about a 5% difference for the techniques that we looked at. So what this is showing, this is again IPC for the different benchmarks. And what I've got here is groups of bars. And again, the thing on the left, the green here is the baseline. And the rest of these bars represent different types or different flavors of the dynamic warp formation algorithm. And what we're changing with it is just the scheduling heuristic. How do I select a warp out of the warp pool and issue it to the pipeline? So typically the warp pool has more than one warp ready to go. And so we have a choice to make. And so what are the different heuristics? So the first bar here is we take the warp that is represented, that has the PC that's the most frequent. So we call that majority. So if there is a bunch of warps, we have numerous warps in the warp pool and they all have the same program counter value, we'll go through those and we'll select those first before we go to the next set of warps that have a different program counter value. We thought it might be interesting to try the opposite, motivated by some work on on simultaneous multithreading. We thought maybe that's the wrong approach. One of the problems we found with this heuristic is that you get some laggards. You get some threads that kind of end up lagging behind the group. And so we thought maybe if we gave them a higher priority by saying let's select the warps that are the least represented and give them a higher priority, maybe they'll catch up to the group. But we found that it doesn't really work because what ends up happening is somebody just scoots ahead. So the next bar here is this minority approach, which you can see the bars here are a little bit lower. The next bar here is we call time, which is basically just a FIFO mechanism. As warps are being allocated, we'll just use a sort of a FIFO ordering, the first in, first out into the warp pool. And so that worked, not quite as well as we would hope, because that would have probably the simplest hardware implementation. That's why we were hoping that would work. What we found actually fixed the problem with Black Skulls was something that used this immediate post dominator as a heuristic for how to prioritize warps being issued out of the warp pool. So really we want to have as few different warps or a few different PCs at a time as possible. That gives us more opportunities to regroup threads into different warps. And so by trying to essentially capture the idea of stopping threads when they reach a post dominator or immediate post dominator, this heuristic is able to help us with Black Skulls. Another interesting heuristic, which is just so simple it seems like it shouldn't work, is to just pick out the warp that has the smallest PC value. That actually seemed to work pretty well too, I guess because of the code layout was pretty sequential. Okay, so again,
It didn't work too well for the Black Skulls.
Pardon?
It didn't work too well for the...
This one didn't work too well for the Black Skulls, but it worked, annoyingly well actually for a lot of things. Because it's just so simple. But the one that seemed to work the best was this post-om priority for black skulls. And so that does help a lot for black skulls. Unfortunately, it seems to lose something on some of the other benchmarks. HMMer and LU and a few, where else was it? I guess Matrix. It seemed to do a little worse with this, and so at least if you look at the harmonic mean, it's about the same. And then if you don't ignore the lane conflicts, it's actually a little bit worse to use this PDOM priority, although it is better for the black skulls. We try random. No, I don't think we did try random. That we should have probably did that. Yeah, but I'm hoping that would be lower. Yeah, we should do that. Thanks. Okay, so again, one of the key differences between the different heuristics here is what they're trying to do is keep more warps with the same PC in the warp pool. So what we've shown, and in the paper we have some extra graphs, just looking at the distribution of the number of different warps that have a given PC value. And so that's one of the key things, is to keep these guys sort of all going through the program sure at the same rate as much as possible, even though they're following different control flow. Okay, so here, it's not enough that we've got this mechanism. Yeah?
Where's the performance loss exactly coming from? Is it due to the loss of locality in the memory system?
When you say performance loss, you mean?
In black skulls, for example.
Mm-hmm.
It's like you said, I'm going to be clever. I'm going to share a warp space with the ALU, and that shouldn't be any worse. And yet we see, whoa, it's lost huge.
Yeah. So well, the thing that we're not even sure if you tried this on real graphics hardware, it would actually behave this way, because these black skulls use a lot of trig functions, and those are implemented in our simulator using libraries. But there's actually, I think, instructions that support for that in some hardware. So a lot of the problem was divergence in those library functions for the trig functions. And so I'm not exactly sure why it should get worse when we're reforming things. I guess it's not really memory intensive. So it's a good question, actually. Why did it get so much worse?
You're supposed to have the answer.
Yeah, you're right. I'm trying to think if we commented on that or had a good. It should uniformly get better, you would think, right?
So when this happens to you, because this did happen to you, you think that it would either be, gosh, am I doing something wrong in my simulation that's causing it to look bad? Or is there really some issue that...
So I think, a key thing can be the memory system, right? As you move things around, the programmer has some idea of these threads are going to all be executing together, so there's some sort of locality. And when you start moving things around, there's a question of whether...
Right, but if you're doing trig functions, you're not...
Yeah, you shouldn't be, yeah. So I agree, and that's why I hesitated to say that.
Okay.
But, okay.
So you considered doing like a rescheduling or reallocation of warps on memory misses?
Yeah.
Seems like those would often happen at the same time. We thought of that. I don't know if we have any results for that. Another thing we've been looking at is actually another problem a lot of programmers complain about is bank conflicts in the local store. So a lot of people writing CUDA programs find that they lose a lot of performance on bank conflicts because you have the SIMD pipeline, it has to access this sort of local scratchpad memory, and that's heavily banked. So they find that's a big problem. So we looked at whether this thing could help there, but we actually found that there wasn't too much of a performance difference when you look at that problem. So you're not really losing, at least for our benchmarks, we weren't losing too much, although other people complain about it. So yeah.
You just have to try to change your code so that you're not crossing,
Yeah, so that's what people do, right? They actually spend a lot of time, and they complain that it's a lot of time to do that. So we don't have the right benchmarks to test that idea, but it's something we're looking at right now, actually. And the memory idea is another thing we'd thought of as well. But I don't think we have any data on that yet. Okay, so,
Another question.
yeah, sure.
So how many warps do you have in the pool for these results?
So this is, I guess it would be 32,
Okay.
256
And you
divided by
found that
16.
That's enough to
Yeah.
get most of the benefit to merge the warps together?
Actually, one of the problems is getting enough threads. So just like real programmers have this problem with when they're trying to write real applications to use GPUs, getting enough threads is actually kind of a limiter. So, but we could have probably had more warps if we
could parallelize better.
Black's codes in particular? Because I can see you can get a lot of threads for FFT, LUN, matrix.
Yeah, that might have been the problem. I would have to double check. Yeah. Okay, any other? No. Okay, so area, we estimate the area here using Cacti 4.2, assuming a 90 nanometer process. And we found that the size of the scheduler here would be 2.4 millimeters. So here's how that adds up. And so if we have 8 cores, we're talking about 22 millimeters. And so if you were to compare that to, say, a high-end GPU like the GeForce 8800 GTX, that would be about 4.7% of the area. And so one of the interesting things that we noticed when we were doing the area analysis is that a lot of the area was really just for the issue heuristic. So, it's really, most of the stuff in that figure of the hardware is actually not contributing to the area. It's that last thing sort of off on the right-hand side that picks out which warp you want to select and issue to the pipeline. And that seems to contribute the biggest part of the area. And so, that's interesting because it's the biggest area. It also has the biggest impact on performance. So that's sort of one of the areas we're focusing on for our future work, is to figure out how we can get rid of this area overhead. Because what the feedback we've been hearing is this is all very nice for control flow, benchmarks, but graphics doesn't, at least existing graphics may not benefit from this. So is it really worth 4.7% area to do that? So that's.
Because if you can flatten your loops with the predicate control flow,
This is still better than.
Number of instructions down by half, which I've seen. All of a sudden, you're like.
We argue this is better than predication. We think predication would be no better than our baseline in this situation.
I'm just thinking of examples where it's just not true. In other words, if I can get 40% improvement by flattening rather than, there's no way this is going to give me 40%.
So what's the 40% from?
Well, it's like keep reducing instructions. Just the instruction size gets smaller and smaller because you're
Okay, maybe.
Okay.
That would sound like an interesting discussion for offline, maybe. Okay, so this is really where we're focusing our future work, is how to get the area impact lower. And so hopefully we'll have something there. So related work, predication is obviously a big one. So here, convert control dependency into data dependency. So we could have used that in our baseline as well, but we argue that our baseline sort of captures a lot of the benefit you would get from predication, we feel. And also, I guess predication, doesn't really necessarily handle the loop issue, although you could probably still have a loop and just predicate the inside of the loop.
So
yeah.
We didn't discuss anything having to do with loops in your work here.
Mm-hmm.
So if a thread leaves the loop, does that mean we're going to feed it with other threads from other warps that haven't left the
So
loop yet?
what we're going to do in our implementation for the baseline is we're going to actually have that thread wait. It's going to wait at the divergence point, right? So.
But it's leaving the loop.
Yeah.
My thought is if it's leaving the loop, we can then take our warps and say, well, I've got 10 warps.
Yeah.
And so far I've got.
Yeah.
50
I understand your suggestion, and it's a good idea, which we didn't explore.
So in the first loop we have all 10 warps going through, but the second loop we only have 7 of the warps going through because 3 warps worth of threads have.
Right. So I guess that's really what we're trying to capture with the dynamic warp formation and scheduling is when those things leave the loop, then we're going to create basically new warps that are full.
Okay.
That's really where we're getting the benefit.
But that hasn't been done yet, or is that?
No, that's really what we're capturing the benefit of the dynamic warp formation. I was thinking if a whole thread exits, right, then you could issue a new thread into a group of threads. So that's not how at least how the CUDA programming model works, but it's in more general you could do that.
I'm saying for this hardware.
Yeah.
The simulations you were doing.
Yeah.
Did you include leaving the loop early, and so you ended up with fewer and fewer.
Yes.
Warps worth of stuff.
Yes, sure.
So that is included.
Oh yeah. So that's one of the key things where the dynamic warp formation actually, again, is getting the benefit. You have one warp, some of the threads leave early, another warp, some of the threads leave early, and you can sort of overlap and merge them together. Okay, so IBM had a patent somewhat similar to the baseline technique, but using actual join and else. They had an instruction encoding to sort of achieve a lot of the benefits of the baseline technique. There's a European patent that sort of proposed at a high level the notion of regrouping for the SIMD branch divergence. And it's sort of a software-only approach, and none of the hardware mechanism I talked about was evaluated in there. And as a patent, it didn't really have any performance evaluations. Really sort of a high level. Could we regroup? There's other ideas that seem related. One is called liquid SIMD, which is the idea that I want to have like a vector instruction set in for say a superscalar processor, but I want to be able to change the width of the vector width from different generations, and I want to not have to recompile. So this was a proposal to do that, but that's not attacking the branch divergence problem directly. And then there's code transformations that you might try to do to eliminate branches that other people have looked at.
So is liquid SIMD a runtime hardware solution?
Yeah, it's kind of it's got some sort of hardware aspect to it, but it seemed more like a sort of between software and hardware type of thing. That was my impression of it, yeah. Okay, so at least for this work, the conclusions are the branch divergence we found could significantly degrade a GPU's performance. Again, we measured 50% performance loss with SIMD width of 16, which would get worse as you go wider. We found that dynamic warp formation and scheduling got us 20% of that back, and then with an area cost of 4.7%. And really, our future work in this area is warp scheduling, area performance trade-off, and I'll also talk about some other future work in this sort of GPU area later. But before I do, I don't know how I am for time. Am I going way over time, or?
10 minutes or so.
Okay. So let me just quickly summarize some of my earlier work. So this is work on helper threads, and published at a variety of places. So there's 3 bits of work here. One is a modeling framework using path expressions to extract important statistics from traditional edge profile data. And in the other 2 papers here are application of that modeling framework. So this was presented at Sigmetrics. And then the other 2 papers here are application of that to either instruction prefetch helper threads or data prefetch helper threads. Okay, so I'm just going to mainly focus on the most recent work there, which is the data prefetch helper threads. So here's just a quick motivational slide. What are helper threads and how do they work? So here's some code from one of the Spec 2000 benchmarks, MCF. And what we have here is a particular pointer dereference that causes a lot of cache misses. So every time you reach this point, you get a cache miss. And this is very irregular address pattern, so defeats sort of stride-based prefetching is sort of the motivation. And so what we're going to do in order to prefetch for this very hard-to-guess address is we're going to create a separate thread that we're going to run on a multi-threaded processor. So here, if we have sort of a high-level schematic for an SMT, simultaneous multi-threaded processor, we have 2 program sequencers. And so one is running the application thread, and then the other one could be used to run these short helper threads. These short helper threads may be 10 instructions long. And so the goal here is when we've identified, and this could be sort of an offline profiling step, you've identified cache miss instructions, and then you find the backward slice for those. Okay, so here I've identified the cache miss, which I'll just label as instruction A. So this is a load instruction. And I look at the backward slice, which is just all the instructions that compute something that this load instruction needs in order to figure out the address that it wants to go and access. So if I go and I look backward through the program, these are the set of instructions that I've identified here. So what are we going to do? Let's imagine how we're going to use this in practice. Let's imagine the main thread is this bus symbol here, and it's like a school bus. It reaches this point in the program, and say we've annotated the main program to have a special spawn instruction. So when the main thread reaches this point, it's going to tell the hardware spawn one of these helper threads. So I'll represent the helper thread here with this little jet symbol. And so the goal here is okay. I'm glad you get it. Okay, so the bus is why is it a jet symbol? Okay, so the jet is going to get to the cache miss a lot faster than the school bus. The main thread is going to take a lot longer because it has to execute all of the program code. The helper thread ideally should be able to skip a lot of the computation that's not related to that cache miss and get there sooner. Okay, so if I go through this animation, you'll see the jet gets there, hits this is the helper thread, it reaches the cache miss, triggers the cache miss as a prefetch, and then the main thread is sort of lagging behind, and it eventually gets there too. It has to actually do a lot more, and when it gets there, it's hopefully it's hopeful that the prefetch initiated by the helper thread has returned from the memory system as sitting in the cache or a prefetch buffer. So the main thread is all happy. It doesn't see the cache miss anymore. So the question is, how do you find these helper threads? And that's what this work was all about. So again, here is just sort of, imagine we're looking at the history of instructions here. You can imagine here's a processor fetching new instructions and committing old instructions, and so this is the trace of instructions. And so we had a cache miss here, and we want to build up, if we look at this, okay, what were all the instructions that led up to this cache miss? So that's the slice. So if we run the program and repeatedly see this same static load instruction that's causing the cache miss, we'll see different slices. So we can build up something called a slice tree, which is the different types of slices we would have needed dynamically in order to prefetch for this load. And so this was proposed by Amir Roth and Gers Soy in some of their earlier work. And they sort of looked at how to optimize. And so, but they did this with an online or a simulation-based framework. And so what we were looking at in our most recent work here was how to construct these slices and predict what the benefit of that will be at compile time using some profile information. Okay, so each node here represents a different slice. So any particular node here would represent a different helper thread, and the number beside it is basically the benefit of using that helper thread. And so we want to construct this tree, which you could construct using program slicing techniques, and then you want to give a value to it. And so the key thing here in this work is how do you find the value to put to each node, which is the benefit I'll see. So just a high level, how do we do that? This framework that presented at Sigmetrics uses path expressions. So path expression is just summarizing all the different ways you can go through a directed graph from one point to another. So it's a regular expression. So you've got your three operators, concatenation, union, and closure. And so here in this example, I've got a path expression summarizing all the paths between S and T. So in this control flow graph here, I've got S and T. So all those paths either, they all start with A. So we all start with A. Then I can go 0 or more times around this loop here, which is represented by this thing in the parentheses. And at the end, I have to go along B, which is over here. While I'm going around the loop, I can go either B to C, or I can go D to E. And then I have to go around this backward edge. Okay, so I can summarize all the paths through the program using that. That's well known. What we did was we said, okay, here's some math I can do with that. So once I use some algorithm to extract the path expressions for the various paths I might want to go between points in a control flow graph, I want to know what's the probability, for example, of going from one point to the other. So we have various statistics. I'm just going to go through an example for reaching probability very simply. What we're going to do is we'll take the path expression, we'll replace the operators with mathematical expressions. So we start off, we replace the labels with the edge probabilities, and then we substitute in these transformations for the different operators. And if you go through all that, you get a probability, which is the probability of going from one point to the other. There's some details, which I won't get into, about how you make sure that that actually represents a probability. So we didn't just look at the probability. We also looked at some other interesting statistics, which are, what's the expected number of instructions I'll execute from one point to another, and what's also the variance in that path. Another thing we also looked at is what is the number of different unique instructions I'll execute going from one point to another, which was useful for instruction cache prefetching. So the general approach here was to just sort of decompose the problem using some probability theory, which the path expression framework made very easy to do, I found.
Did you look at expected latency?
Yeah, so that kind of fits in with the expected path length, but then you have to sort of factor in a CPI per basic block. So yeah, I was looking at it. Yeah, it gets a little bit trickier.
CPI?
Cycles per instruction.
Okay.
So this would be the number of instructions, and then have to multiply it. So one interesting thing is we started off looking at just single edge profiles, so the probability of going from one basic block to another. And there is, then we started to analyze what are the inaccuracies in that. And one source of inaccuracy is that branches are not sort of random things. They tend to be correlated, which is what all modern hardware uses, exploits that for branch prediction. So we went to higher order control flow graphs, and we found that you can just take the same path expression framework and just sort of evaluate the paths in this higher order graph. So here is a a higher order graph where instead of having a single node represent a basic block, it's now going to represent a transition in the original control flow graph. So here, this one block in the center means I went from basic block 8 to basic block 6. And then I'm going to go from basic block, and then, so the next thing here, the edge between that says, if I was previously at 8, I'm now at 6, and now I go to 16, what's the probability of that happening? So it's sort of a second order probability. Sort of incorporate some of the history of how I got to the current basic block into this profile information. So we found that if you do that, you can get better accuracy of modeling of the control flow. And so this was in the ICS paper, and more recently I've extended this to higher order graphs, and you can basically get most of the control flow correlation by extending this to higher orders. Okay, so I think that was the quick, run through many years of my life. Okay, so
On the data prefetch, did you actually have real life examples where you wow, that's a lot faster?
oh yeah, for helper threads help a lot for data prefetch. So for MCF, I can't remember the numbers, but we were getting double-digit % increase in performance with a reasonable memory system.
And I guess the question is, the other comparison is to use that helper thread, that other core to do other work rather than helper work.
Okay, yeah, right. Okay, so there's always, so the argument is, what if I have a workload that's single-threaded, but I have multi-threaded hardware, right? But I really just want to run this one thread, but I want, huh?
More users. No.
Okay. Well, that's a whole philosophical debate, right? So, but there, this was the starting point of the research was, if that's the scenario, what would I do?
I've got some cores that are just sitting there, snoozing because they don't have anyone to go out to a date with.
Right. Yeah. So we were actually assuming SMT or simultaneous multithreading rather than multi-core, but yeah, basically that's the idea. Yeah. So future work. We're looking, again, I mentioned this already, looking at improving the efficiency of the dynamic warp formation, at least the area efficiency. Also, we're looking at scalability of stream processors. So if I write the program with the sort of current assumptions about the hardware, how will that scale, or what can we do at the hardware level to make it scale better? Also, looking at heterogeneous multi-core, which is if I say take a CPU and a GPU and stick them together, what can we do with that? We were doing a little bit of work. We were thinking about doing work on automatic parallelization of GPUs, which is seems like a really hard thing to do. We started looking at that, and might still continue to look at that. Another sort of totally different topic from the GPU stuff is carrying on the sort of analytical modeling stuff, like with the helper threads. And that's we've been looking at analytical modeling of processors, and here the goal is to shorten development cycles. If it takes me years and years of modeling in a performance simulator to figure out what I want to actually build, that's time to market pressure. And process technology is changing so quickly that my assumptions when I start developing the processor and when I actually finish it are going to change. And so I might have actually started designing the wrong thing, and then have to halfway through actually building it change things in order to build it. So the goal here is, can we get through the early stage development faster, or have a better idea faster, so we can actually start building the chip sooner? All right. If there's any questions, any more questions, glad to take them, and thank you for your time and for going to talk.
For your SMT work, Pentium 4 has a hyper-threading.
Mm-hmm.
Is that the sort of thing you were
Yes.
referring to as actual implementation?
Yeah, that's what we're considering.
Because the other question is you're also cheating your main thread sometimes.
Yes, so that's true, and so there's a balancing act there, right? So you want to use this judiciously, right? So only when there's actually a need for, because you are stealing resources from the main thread.
So the next question is, you're actually doing processing that could be used by the main thread aside from the cache
Yes.
situation, or the prefetch situation.
Yes.
You could actually say, well, I've got the answer 27.
Yes, right. Yes,
so
and
why don't I pull those instructions out?
yes, and some people have looked at, could I reuse the result that I had generated there? So a lot of this was closely related to something called speculative multithreading, where people were actually, that was the whole goal, was to actually spawn off a thread, compute something, and then actually use that result. in the main thread.
How did that work out in real life?
To be determined, I think, still is the.
Turns out it's very hard to communicate the results
Yeah.
and merge them back in.
Yeah.
Build the hardware for that.
Yeah.
That hardware turned out to
Yeah.
be quite complex.
Yeah.
But people are still researching.
I think people are still working on it.
Okay. Multithread communication has to go through.
So people, I think some people propose extending cache coherence mechanisms to do this.
I see.
Right.
But that may cost hardware area.
Yeah, yeah. There's definitely trade-offs. Yeah.
So you showed this bar graph with a lot of different variants of dynamic work formation.
Yes.
And a lot of variance in the result. There was just one baseline bar.
Yes.
How much are there different ways of scheduling works with the static work formation?
Yeah, we just sort of round robin scheduled for the baseline. I imagine there could be other techniques. So if you look at, SMT processors, they have the scheduling problem. You could round robin between the threads, or you could do something more sophisticated. So for example, one proposal for simultaneous multithreading, like hyperthreading, was to use something called ICount, which is schedule the thread that has the least number of instructions in the pipeline. So that tended to get better overall performance, for example. But we haven't really explored that. All right, thanks.
Any other questions?
Okay, thanks.
Thanks a lot.
Thank you.